Welcome to the Advanced Sienna Modeling workshop. So I'm David Schaefer. I hopefully am familiar from the introductory video on Sienna models. And I'm joined here by Cassie McMillan, who's going to be helping. And so just a little bit of background about us. So I've been working with Sienna models for at least a dozen years now. I normally look at adolescent networks and their change over time and change in some health behaviors. More recently, I've been looking at prison networks, how they change over time, and broadening outcomes to look at things like ethno-racial segregation and intergroup contact. Cassie?
Yeah, hi everyone, I'm Cassie. I've also been interested in networks for almost a decade now. A lot of my research is really interested in thinking about the ways that our social networks both reproduce and challenge different kinds of inequality. So for instance, in particular, I've examined a variety of different types of adolescent friendship networks, as well as adolescent bullying networks and adolescent dating networks. I've also looked at patterns of international migration as networks as well too. So thinking about how the patterns of people moving can be conceptualized as a network as well. And across all of these different kinds of projects that I've worked on, I continuously apply and develop different types of statistical network methods, such as stochastic actor-oriented models. And in particular, in my recent work, I've used SAOM to do a lot of different kinds of simulation-based work.
Great. So we are, we will be, the rest of this video, we're going to talk a little bit about kind of some overarching principles and guidelines to keep in mind when kind of taking Sienna models, or as Cassie properly called them, stochastic actor-oriented models. As we take those further, just some considerations to keep in mind. And then we'll go through a lab. We've got a couple of labs, one that looks at asymmetric peer influence and how we can test whether peer influence on increasing or adopting a behavior differs from decreasing or ceasing a behavior. So we'll go through that, and then Cassie will talk about how we can use Sienna or Zounds for simulations, such as if we want to consider the implications of different kinds of interventions. Okay, I hope you enjoy it.
Today we're going to focus on two extensions to the basic Sienna model. Now, to provide some background, it's important to keep in mind exactly what a Sienna model is. And specifically, what I mean is that the model is estimated as a stochastic actor-oriented model. And that actor-oriented or actor-based part is critical. What the model does is it breaks down the observed changes into a series of smaller microsteps during which actors change their behavior or they change their network, one tie or one step, one level of behavior at a time. So really, to understand any kind of, the model itself, but also any kind of extension to it, this actor perspective needs to be kept in mind. This is really a decision model where we're trying to model what rules or kind of what information is used and how important is that for any given change that is observed. Okay, so to estimate this model, we use a simulation-based algorithm. Okay, this is kind of built into our Sienna machinery, and it's flexible in some ways, although there are also limits on what can be done. Okay, so one of the limits is that no matter what, the dependent behavior is going to be centered. We'll talk a little bit more about that later, but it's something you can't get around, and so that comes into play in interpretation. It also comes into play in a more kind of cumbersome way when we're doing simulations. We also have to work within the scope of effects that are built into our Sienna. Okay, there's a number of selection effects, a number of influence effects, and some of them get quite detailed, but We're limited to those that exist, that we can easily add into our model, or we could create our own. If you know how to work in C++, then you can go in and create your own. It's a little bit more involved than simply specifying effects, but there is that possibility. Other parts of the algorithm are less flexible. Okay, so for instance, one part of the algorithm is that actors are randomly chosen to act and either change their behavior or change their network. Now we can adjust the probability with which actors are selected, but we can't get around the fact that actors are going to be randomly selected to make that change. Okay, other things like only one tie change at a time is possible. That's not something we can really easily work around, if at all. And so if you're thinking about simulating network evolution and or behavior change, then parts of this process are going to be kind of set and fixed, and you can't get around them. Now there are some ways to get creative. I think we'll show a little bit in the lab about how to get creative with changing strength of peer influence across time. There's other ways to get creative if you want to. We're not going to go into a bunch because kind of the needs and the workarounds are highly unique and case specific. So we're going to, one of the things we're going to do today is talk about how to differentiate whether peer influence differs in strength for increases in behavior versus decreases. And as a reminder, during a microstep, when an actor is selected to change their behavior, they look to the behavior function and use that to determine the utility of increasing their level of behavior 1 unit, staying the same, or decreasing 1 unit. So there's 3 possibilities. If they're at the minimum or maximum, there are only going to be 2 possibilities. So what we typically do is assume that the strength of an effect, like peer influence, is the same for increasing one's behavior versus decreasing versus staying the same. Okay, that's kind of the simplest way to specify a model. And when we, in the earlier examples, when we set an effect for peer influence or something, we're making that assumption. Okay, now we can relax that assumption. Okay, we can actually test whether this is, in fact, the way the network and behavior are evolving. And we're going to do that by setting up the behavior function a little bit differently. Okay, so the behavior function is typically set up with evaluation effects. Okay, that is, actors evaluate the utility of each possible change using only evaluation effects. And those evaluation effects are applied whether the actor is considering increasing or decreasing or staying the same. The same effects are used. What we're going to do when we want to distinguish increases or decreases in behavior and differences in effect strengths, we will add creation effects and or endowment effects. Okay, and what this means is, for instance, if we want to consider whether peer influence differs in strength, we would add a peer influence effect for behavior increases, for example. And that effect would only be considered for increases in behavior. Okay, so if we wanted to test whether decreases in behavior driven by peer influence are different from increases in staying the same, we could include an endowment effect. And the way these effects work is, let's say an actor is at a certain level of behavior. When they're considering, for instance, the utility of staying at that level, they consider the evaluation effects. Okay, calculate the expected utility of that level of behavior for a particular set of effects. Now, when they're considering increasing, the actor is also going to consider those evaluation effects, but in addition, they will consider a creation effect. So for instance, there might be a creation effect specifically for peer influence. Okay, and by contrast, if we're considering decreases, then we can specify an effect that's just there for decreases. And so when an actor is considering whether to decrease their behavior, again, they look at, consider the evaluation effects that are in the model, plus an extra effect or more for that only apply to decreasing their behavior. Okay, let me give you an example of how that might look. Okay, so here we have a set of common effects that are in behavior functions. Okay, we're always going to have a linear term, maybe a quadratic term, and maybe effects from other individual attributes. Okay, typically we put these in the evaluation function, and they again inform or are evaluated for every possible change, increasing, decreasing, or staying the same. Okay, we can keep those in the evaluation function, and again, we're constraining their effect to be the same across those different types of change. Okay, now the conventional approach is to also put the peer influence effect in this evaluation function. Okay, and when we do that, then this set of effects and their corresponding parameter estimates are used for evaluating all three types of change. Okay. Now, when we want to start differentiating the direction of effect, okay, we can keep these common effects in the evaluation function. Okay, let's maintain the assumption that these apply the same way to each kind of change. There are three ways that we can specify differences in behavior increases from decreases. The first here is treating increases and decreases independently. Okay, so what this specification is going to do is it's going to enter separate effects in the creation function and in the endowment function. Okay, so what this means is when an actor is evaluating behavior, if they're evaluating increases, then they'll use this effect. And remember, each of these effects is going to have a corresponding parameter value. Okay, so we can estimate separate parameters for increases and decreases. So in this specification, to consider an increase, an actor considers the value of average similarity for increases, okay, weighted by the parameter that's associated with increases, in addition to these effects up here. Okay. Now, if an actor is considering decreasing their behavior, they'll use the average similarity effect, but it has its own parameter estimate, a second parameter estimate that's only considered for decreases. Okay, so to consider the value of the utility of decreasing their behavior, the actor would consider the average similarity of their alters, weighted by that parameter estimate, plus these linear, quadratic, and other effects that apply to any behavior change. And then if an actor, to calculate the utility of staying the same, the actor would only consider these evaluation effects. Okay? Now, this type of specification helps to answer a particular set of research questions. The first question is influence present for increases, and that's indicated by this average similarity effect that's only calculated or evaluated for behavior increases. And then correspondingly, we have a parameter that gets at is influence present for decreases. Okay, so we look separately at these two parameter estimates to determine if each type of peer influence is present. Now, a second approach to differentiating direction of peer influence is what I'm calling the deviation approach here. Okay, and what this does is we specify an evaluation effect for peer influence, such as the average similarity effect. Okay, and this is applied to any behavior change, right? Increasing, decreasing, staying the same. Okay, then we add a second effect that gets at whether or not, that's only considered when an actor is evaluating a decrease in behavior. Okay, so this is a deviation effect. And what it's doing is it's testing is the strength of peer influence for decreases different than for increases or staying the same. Okay, so what we can answer with this specification is this first parameter can tell us, is influence present? Are actors changing to be more like their alters? And then B, does the strength of peer influence differ for decreases compared to increasing or staying the same? Okay. Now we have a variation of that called deviation, the second form of deviation, where we're again including an evaluation effect that gets at overall peer influence, and then this second effect only applies to actors considering increasing their behavior. Okay, and here again we're asking, with the overall effect, is there peer influence? And then with our deviation effect, we're asking, is the strength of peer influence different for increases relative to decreasing or staying the same? Okay, we'll show a little bit more in the lab about how to specify this and a little bit more about how to interpret it. Okay. Now, any effect can be specified using these different effect types: the creation, endowment, and evaluation, in the network function or in the behavior function. I shouldn't say any. There are a very small number that aren't differentiated like that, and the manual will have that information. Now we can only use two types. So as you saw in the previous examples, we'll have one effect, the evaluation and creation, but not all three types. Okay, the model's not estimable if we tried to put all three types in there. So how do we decide which ones to include? Well, as shown on the previous slide, they answer somewhat different research questions. And so depending on your specific hypotheses and particular whether you're wanting to test the presence of peer influence on increases versus decrease, or alternatively, does the strength of peer influence differ in strength for these different types of changes, up or down, then you would want to include different versions. Okay, the evaluation plus endowment version, for instance, will tell you overall, is there peer influence, and then does that differ in strength for decreases? Okay, which is a slightly different question, right? Than does peer influence exist in increases and in decreases of behavior? Okay, so thinking very carefully about the research question you're posing is important. The second issue is power. Okay, so when we're differentiating increases from decreases, we're losing some power already because we have fewer instances of observed change. When we break up those instances into distinct types and try to estimate parameters for each type, we're losing power. So we're at a somewhat of a loss already in discerning effects. Okay, now when we're calculating the statistics behind these three different types of effects, all actors contribute to evaluation effects, whether they increase, decrease, or stay the same. Okay, so when we're calculating peer influence using an evaluation effect, we're looking at every actor and how similar they are to their alters across time. For increasing or decreasing, we are only looking at those actors who actually increased or decreased to calculate these statistics. And so we have somewhat less power for those than we do overall. So what this means is if we're using the first specification, the independent specification, where we have actors increasing and actors decreasing, that's actually has the least number of observations because we're ignoring anybody who stayed the same. Okay, so we have the least kind of power with that effect. Okay, so I've also found sometimes there is some, with these kinds of power issues, there's some trial and error, so to speak, in that, you can try one specification and you might not have the power to detect it. You might see your standard errors blow up. And another specification might have a little bit more power. And so sometimes there's a little bit of trial and error that you go through. Okay. All right, turning to simulations, I'd like to first begin by reminding or thinking about why we do simulations. Okay, and simulations, from what I mean by simulations is we have an estimated or observed network, and we want to take those estimated parameters and the network and simulate what networks would look like based on if the rules specified by that model are in operation. Okay, so we already do this, with good Siena model estimation and fitting. We already do this in our goodness of fit step. Okay, as we take our observed model and make sure it represents the observed networks over time. We also do this with decomposition. So for instance, if we wanted to know how much of similarity on a behavior is due to selection or peer influence, then we can use simulations to evaluate the relative contribution of different model effects. The third purpose that we're going to focus a little bit more on today is interventions, or we say, well, what if something worked differently? What if we intervened on this network and changed something about the rules actors use to select one another, or how they influence one another, or whatever kind of theoretical question we have. Okay. Now, in thinking about simulations, it's useful to think about the two parts that we have, these two main parts. So one is we have some initial conditions, right? There is some hypothetical world that exists and that we start with, and that's composed of actors. There's some number of actors. They have some attributes. There's some distribution across that population. Okay, and then there's a network. There's some number of ties, and they're arranged in some way, and maybe there's multiple kinds of ties. I mean, you can think of this in many ways, but all of these things are fixed at some starting point. Okay, and then second, we've got rules. Okay, in the case of a Siena model, these are the effects that are in the behavior function and the network function that guide behavior, and those effects have some parameter estimates or values associated with them that get at the strength of those rules. Now, there are also rules that are kind of built into the our Siena algorithm. There's this process of selecting actors randomly for changes. There's a rate function that determines that, and so there are these other rules that we have less control over those rules, in the sense that while we can add effects to a rate function to make some actors more or less likely to be chosen, we still have to have a rate function and some randomness in there. Now, the ability to do simulations, or kind of how easy it is to jump in and do that, differs greatly across these different types. Okay, so when we're doing goodness of fit, it's really simple, relatively speaking, of course. We take an estimated model, and we take an observed network at wave 1, and using that, we simulate over and over again what the network, or what kinds of networks that model would create. So we're not manipulating anything, right? We're just taking our estimates and observed network and simulating from there. Okay, super easy. For decomposition, it's still simple, relatively speaking. In this case, we're keeping the initial conditions the same. We're conditioning on the first network, and then we're manipulating the rules by which actors are changing either their network or their behavior. And here the manipulation is very simple. We will systematically set some parameter values to 0, right? So we'll knock out some effects, do some simulations, and come up with a, calculate how much homophily there is within a network based on, some different sets of parameters being set to 0. Okay, and you can see Christian Steglich et al.'s paper for a good example of how you'd want to do that. Okay, now for interventions, things get a little bit more complicated, or they can, depending on what you want to do. If you want to manipulate the rules, that is super easy, right? If you want to just manipulate parameter estimates and look at how manipulating, for instance, maybe the strength of peer influence. What if peer influence is absent? What if peer influence is twice as strong as observed in terms of the parameter value? That's pretty easy. Okay, you can set that up, change that very easily, and run your simulations and calculate whatever output statistics you're interested in. If you want to manipulate the initial conditions, that gets more complicated. Okay, so what do we mean by manipulating initial conditions? Well, in the example we're going to talk about later, we want to set some individuals' behavior to 0, right? So we've got some intervention. We come in and we set some people's behaviors from whatever level they're at down to 0, and then we look to see if does the prevalence of this behavior, how does it increase across time? Okay, we could also think about changing. So that's changing the level of the behavior, the distribution of the behavior. We could also think about changing the network, right? We might want to remove some ties. We might want to create some ties between actors. You could imagine interventions that create access or maybe put actors into groups. Any of those are going to change the initial conditions. And that introduces complications because the initial conditions are used to inform parts of the Siena estimation algorithm. So on one of the big ways is through centering. Okay, if you change the initial distribution of a behavior, then when Siena centers that variable and includes it, then it will be affecting the value of the statistics for that behavior. Okay, so for instance, there is the absim statistic for behavior, for peer influence on a behavior, is centered by the overall mean of the behavior as well as the mean within dyads. And so when you change that, you're changing the overall similarity. And so what that means is that the exact same parameter value will be evaluated differently depending upon where this variable is centered. Okay, so that's something to take into account with simulations in the sense that what you want is that your manipulation of, say, the initial level of a behavior is the only thing you change, right? And you want to compare one scenario to a second scenario. Okay, but if you're changing that behavior and the strength of the effect also gets changed because of this centering, then you're actually introducing a confound to your design. Okay, so we want to avoid that. So we've got some the workarounds to account for that involve creating a new effect, but that can be done. But it needs to be taken into account and addressed. Secondly, the outdegree term in the network function, as well as the linear and quadratic terms in the behavior function, those all dictate the target distribution of the network in terms of density and the behavior in terms of its distribution. So you could start with very different networks and very different behaviors. And if you simulate the same model with that outdegree and linear and quadratic term set at the same levels, you'll reach the same outcome, right? Because those dictate where the model is trying to go. Okay, so what that means is again, if you manipulate something, but don't think about what this out degree and linear and quadratic terms are doing, then you tend to see the model trying to get to the same place, and very small differences in your observed and in the outcome you're interested in. Okay, now there's so what do we do about that? Well, we have to have these terms in the model. So the question that becomes, what distribution do we want to target? We want the model to kind of aim toward. It could be that we, want a target distribution that looks like the time one distribution that we're conditioning on, or at least maybe not want that, but one strategy is to say, well, let's have those parts of the model not lead to any change in the distribution, right? We've got a distribution at time one. Let's keep that the same, and then have look at what differences in manipulating other kinds of aspects of the model, the selection rules or behavior change rules. How do those changes affect the ultimate distribution? Okay, so one idea is to adjust these such that they maintain what's observed at time one. There might be other kinds of distributions that you might aim for as well, but it's important to keep in mind what should the model do kind of in the absence of your manipulations. Where will it go? Okay, so some final thoughts before we get started with the lab is that when doing simulations, we could and what's often been done to date is to estimate a model on some observed network and then manipulate parameters or initial conditions from there. And that provides kind of some level of realism to the network in the sense that it's it's still a model, but it's somewhat grounded in what's empirically observed. It's also possible, though, that you might want to create your own network. Just make up a network with certain properties, come up with certain rules that you want to guide change in that network or that behavior, and simulate models based on that. That's perfectly fine too. A challenge with that, is your model's only as good as what's in that model, and the set of rules that you use to guide it. And so taking that kind of approach, you would want to be very clear theoretically what processes you are accounting for, what processes you're not, and how those work together. In either case, to do simulations, you're going to start with creating a Siena data object the same way you would when you're fitting the data, right? So you're going to create a couple of networks, a time one and a time two network, and maybe a distribution of behavior as well at each time point, and make sure that those each differ by at least one tie or one behavior change, or else the Siena algorithm will throw up some errors. So you're going to want to create a time one and a time two, even though you're doing simulations and really don't need that time two. That's just the way that the data setup works. I also want to mention that in these examples, as well as the lab to come, we're using the AvSim effect for peer influence. There's no great reason for that, other than it simplifies some things during presentation. The steps we go through can be used in principle with these other estimates or other ways of measuring peer influence. Just keep in mind a couple of things. One is that the sim terms, AvSim and TOTSim, those are capturing a different theoretical model of peer influence than AvAlt and TOTAlt. The former get more at assimilation or becoming similar to others, whereas the others get at whether actors are pushing one another toward or away from the mean. Okay, so the interpretations will differ, and then the scripts will necessarily differ as well. And I've tried to make some comments in there where they will differ, but keep in mind when you're calculating effects that these do have different formulas, and you can see those in the Siena manual. And in that regard too, I want to strongly emphasize that when you get to more advanced kinds of Siena techniques, you really need to be intimately familiar with how the model works and how it's estimated and how effects are calculated. So a general rule of thumb I tell my students is, don't get into these advanced techniques until you're able to go to chapter 12 of the Siena manual and look at effects and understand how those are calculated. You need to do that to be able to understand how the model's working and how to interpret the results of your simulations, as well as any kind of model estimates you are using. So understanding those effects and then the estimation method behind that is critical when you get to that interpretation step. And with that, let's go through some examples.
Welcome to the lab portion of today's tutorial. I'm going to begin by walking through how to set up and run a model with asymmetric peer influence, and then how we can interpret those results. Okay, you should have the script, and I'm going to assume some familiarity with our Siena. That is, you've set up and run a model before and interpreted it, and so we're going to build on some of the things that you should already be familiar with. So we're using the S50 data that comes with our Siena. So I'm going to get that set up. We're using 2 waves of data here, and just looking at drinking as an outcome. Now notice I created the print 01 report. It's always a good idea to run. It's a way to ensure that Siena is reading the data the way you intend it to. So it's always a good idea to review that and look at the descriptives it provides. Okay, I'm going to set up my effects. I'm calling this controls, my controls, because as we'll see in a little bit, we're going to add different kinds of effects to this to estimate the different kinds of peer influence. Okay, let's begin by taking a look at this. If we look at my controls, we'll notice, right, it lists all of the effects here. These are all the kind of pre-calculated effects that Siena will create based upon the data that you provide. What I want to point out in particular, right, is we've got our effect names here. We've got our short names. You should be familiar with those. For each of these, so for instance, let's look at reciprocity. Notice that we have 3 effects, right? Reciprocity is in here 3 times. The difference here has to do with this type column. And this type says eval, endow, and creation. Okay, normally we just look at evaluation effects. That's kind of the default. And when we're wanting to constrain peer influence or any effect really to be the same for decreases or increases in behavior or adding a tie or deleting a tie, we use evaluation effects. If you don't specify anything, this is what gets used. But there are endowment and creation effects, okay? And these are what we're going to be using when we get to specifying asymmetric peer influence. We could do the same for adding and keeping ties if we want to distinguish those 2, but that's for another tutorial. Okay, so with that in mind, I'm going to specify a few controls that will be common to all of our models. And then I'm going to set up a series of models that specify peer influence through the different ways we covered. Okay, first is what you're probably already familiar with, the conventional specification of peer influence. So what we're going to do here is use the avsim effect for peer influence, and that's it. We're going to leave this type that I mentioned earlier We can leave it absent. We could specify it as eval, but the default will be eval. Okay, so let's run this. Okay, we run this, and if we look at what this object is, we'll see it lists all the effects we have as controls, and then we have this drinking average similarity at the bottom here. Okay. All right, so that's our conventional model specification. Now, if we want to specify increases and decreases on behavior, peer influence effects separately, we're going to go to this second specification here. Okay, we're again going to create an effects object that already has our controls, and then the effect for increases in behavior, it looks a lot the same as before. Just at the end, we're going to add this type equals creation option to it. Okay, that will be the effect that captures increases in behavior only. This next effect captures decreases in behavior only. Okay, and when we look at this, notice two things are different from before. Okay, first of all, we've got two effects here for peer influence at the bottom. And we've got this type column now that tells us that one of these is an endowment effect, one of these is a creation effect. The rest of these are either evaluation effects, which is the default, or our rate effects also have their own type. Okay, so that's how we know we set this up properly. All right, the third specification, again, we create our controls. Here we're going to use the evaluation effect to capture the overall effect of peer influence. Again, I don't need this type at the end, but it helps to make it clear. And then this next effect looks at deviations from peer influence for decreases in particular. Okay, so we've got that. And again, we can review it. And we see that we've got two effects for peer influence again at the bottom. One is an eval effect and one is an endowment effect. All right, lastly, we're going to look at the alternative deviation specification. Okay, that uses one eval effect and one creation effect, right? So this time we're testing for overall peer influence with the evaluation effect, and then the creation effect tests, well, is it different for increases only? Okay, and then if we look at these, again, we see two effects at the bottom, one for eval, one for creation. Okay, so those are our model specifications. I'm going to skip over looking at them again. Now we're going to set up and run our model. Okay, so the model setup, our algorithm looks just the same as in other uses. And we're going to set up and run the same model. The only difference is which effects object we use. And I've already run these. I'm going to run one of them because I think it's going to show us something interesting. Our window pops up. Our peer influence effects are these last two, right? 11 and 12. And I want to show you something here. Effect 12 is getting really big. 20, 20, 19, 22. That's a big value for peer influence. This isn't going to be a very good model, okay? I tell you that now because this is a toy data set, right? Took 20 seconds to run. Many of your data sets will be much larger and take hours, if not days, to run. Pay attention to those estimates and deviations as they're going along. And when you see something that gets really, really, really out of whack, sometime in that second phase, really high values that just keep getting larger and larger, that's a sign your model's not converging. You're not going to have a very good set of estimates. You might want to stop it there and rethink your model before continuing. Okay. All right, so now let's look at our results. This first set of output is our conventional model. Okay, and here, notice that we've got a positive estimate for our peer influence effect, a not unreasonable standard error. This would be a significance level of a t-value of maybe 1.5, which isn't conventionally significant. But I'm not going to worry about that now because this is, again, a toy data set, and we're only using 2 waves of it. So assuming this were significant, this would be evidence of peer influence, right? Our positive estimate is a sign that actors are becoming like one another in terms of drinking over time. Okay, let's look at our independent specification here. Okay, now this one was also pretty bad, right? Our endowment and creation effects, one of them got really big with the huge standard error. Actually, both standard errors are quite big. So this isn't a great model, but we can still talk about what it means. Okay, a positive creation effect, this latter effect here, if significant, would be indicative that there's peer influence on increases in the behavior only. Okay, so when actors are considering increasing their behavior, their alters level of the behavior is influencing that decision. Okay. The endowment effect, effect number 12 here, is a similar kind of evaluation, but again, only for decreases. So when actors are considering their decreasing their behavior, how much do they consider their alters behavior? And if we had estimates such as this would tell us that peer influence on increases is much stronger than peer influence on decreases. Okay, peers are much more important for adopting or increasing the behavior than vice versa. Okay, so we can interpret those two separately. That's the key point here, that they measure those differences separately. All right, let's look at the deviation specification. And what this model is doing is the evaluation effect is capturing peer influence for increases, decreases, and staying the same. Okay, and a positive effect here indicates there is peer influence. Okay, again, assuming it's significant, we would infer that there is peer influence. This endowment effect is negative. Okay, so what that tells us is that the effect of peers on peer influence when considering decreasing their behavior is weaker than for overall. Okay, so for decreasing their behavior, actors consider both of these, the eval and the endow effect. You consider them both in conjunction. So this negative effect tells us it's weaker. If this were 0, it would be indicative that peer influence on decreases is no different than peer influence on increases, right? This is a deviation score. Okay, so a 0 doesn't mean there's no peer influence on decreases. It means peer influence on decreases does not differ from peer influence on increases or staying the same. And then lastly, if this effect were positive, it would tell us that peer influence in decreasing one's behavior is stronger than peer influence on staying the same or increasing. Okay. All right, our last model is another deviation. This time we are looking at how increases in the behavior differ from decreasing or staying the same. This one's a weird model. Okay, this is actually saying that the main evaluation effect is negative, meaning there's not peer influence. There's actually evidence that individuals change to be different from their alters. Then this creation effect says, again, it's a deviation from this main effect. It's positive, which tells us that peer influence on increasing one's behavior is stronger. Okay, and in fact, it's much stronger than an evaluation effect. So what we would conclude would be that peer influence on increasing behavior is strong, is present, whereas peer influence on staying the same or decreasing is not present. Now, in my experience, I'll just mention that I have found that this type 3 effect tends to work the best. Again, that's my anecdotal experience, but you get a little bit more power. The evaluation effect considers staying the same, which gives you more, in effect, more observations because you're considering what happens with people who stay the same, and do people stay the same in their behavior to be like their peers versus increasing or decreasing to be less like them. So it gives it a little bit more stability to the estimates. So I would have expected that to work here as well. And I think with different data, we would see that with the more larger data set, we would see the more stability here as well. Okay. All right, so with that, I want to talk about how to interpret this, because I think you can interpret this based on the coefficients alone, and their sign and strength. And sometimes that might be easiest, to be honest, but a good visualization also goes a long way. And so this last bit of script sets that up. So I'm using the script that creates a ego alter influence table. And the idea here is we create some hypothetical scenarios where what if ego has a given level of behavior and alters have a given level of behavior, and then ego is considering what level of behavior to adopt, right? Stay the same, increase, or decrease. And we calculate what would, based on the estimated model, what would the predicted utility from the behavior function be for each of these possibilities. And we do this for the full set of possibilities, right? So for every potential value of ego's behavior, alters behavior, as well as every possible change. Okay, so we've got a function that does that. I'm first going to create a couple of functions that bring in effects that are relevant when changing behavior. That's the linear effect, the quadratic effect, and then the average similarity effect. Okay. In the second specification here, we've got those, plus we've got an effect for the endowment effect. So I should mention I'm using the deviation model up here, model 3, which gave us something that looks a little bit reasonable. No wild crazy values. Okay. If we're using some kind of different model specification, a different value of peer influence, a different measure of peer influence, or one of these different specifications for increases versus decreases, this is going to look different. Okay, these functions will be different. So these are not one size fits all. Okay. These functions are based on, these are the equations in the Siena manual. So you should take a look at that and understand that for any kind of work within Siena. Okay, so we're going to calculate or create those functions. And then I'm creating a second function that actually creates the ego alter influence table and then visualizes it. Okay. So let's create that function. Okay, and then we're going to feed in the hypothetical values. Okay, so these first two, the average of our behavior and the similarity, come from that print 01 report. Then we've got our estimates. And then we've got the hypothetical scores for ego and alter that we want to consider, right? So in this case, drinking ranges from 1 to 5. And so we're putting in 1, 2, 3, 4, 5 as the values. And then we're going to calculate the range, which is something the average similarity statistic needs. All right, and now we're ready to plot. Okay, this is our plot. It's really kind of ugly. Let's stretch it out a little bit and see if it makes a little bit more sense. I noticed my legend didn't show up, so I'm just going to run it again. And there it is. Okay, so what we have here is different scenarios. Okay, and because we're considering, right, ego's behavior change and whether it's an increase or decrease, we need to figure out where, it's important to know where ego currently is and where, again, whether each potential behavior is an increase or a decrease from the current state or staying the same. So we've got separate panels for, here, let's assume ego is currently a 1. Okay, and if ego is a 1, ego can either stay the same or increase by 1. And so we've got lines here that represent the calculated utility of each of those. Okay, so let's consider staying the same. Okay, if ego stays the same, then depending upon alter scores, we get decreases in this calculated utility. Right? If alters are a 1, then ego is most likely to stay the same compared to if alters are lower. All right, so this is evidence of peer influence. Ego is only going to stay a 1 or most likely to stay a 1 as alters are more similar to ego. Okay. Now, the green line is the scenario when ego is considering increasing their behavior by 1 step. Okay, so going from 1 to 2. And here we see the highest utility occurs when alters are also at 2, right? So this is, again, this is peer influence. This is most likely when alters are at 2 and less likely otherwise. Now, the real way to consider this is within a value, right, of alters, right? Because alters are at a score, right? Alters have a value. And so ego is considering kind of conditional on that. If alters are at 1, then ego is most likely to stay at 1 because that's the highest predicted utility. If alters are at 2, ego is likely to increase from 1 to 2. And for any alter scores above there, ego is also more likely to increase their behavior. Okay. If we jump over to ego is currently at 2, then we see a similar pattern, right? If alters are at 2, then the highest utility is for staying the same. If alters are a 3, then ego is most likely to increase to a 3. We also have the possibility, though, of decreases, right? Ego could jump down to 1. And in that case, this red line comes in here. And we see that actually ego is more likely to decrease 1 step than go in either direction. Okay. All right, so we see now that depending upon, again, the value of alters, ego's behavior is likely to follow suit. Now, in this scenario, peer influence was asymmetric. It's stronger for increasing than for decreasing. And we can see that here, right? So when considering decreasing, the utility of decreasing versus staying the same, it's about, what is that, maybe 0.2 difference, okay? If we go up here to the difference between increasing to be like alters versus staying the same, that's a much larger difference, right? The difference in utility is about 1. Okay, so that's maybe about 3 times more likely. This is maybe 1 or 0.5 times more likely to decrease than to stay the same. So that's that asymmetric part. So peers who are higher in value than ego have a stronger pull than do peers who are lower. Okay. Now I want to show you just a couple of alternatives, other findings we might have seen and what those would have looked like. So one possibility is that there's no peer influence on decreases, right? How would that show up in our estimates? Okay, well, our beta for the evaluation effect would be the same, but our beta for peer influence on decreases would actually offset that, okay? And negative 4.9 would perfectly offset that. So let's look at what happens under this scenario. Okay, here we see the same pattern. For instance, when ego score is 1, we see the same pattern. When we start to consider decreases, right, the plots with these red lines, notice that this red line has the same shape, in each plot. Okay, what's happening here is that alters have no effect whatsoever when considering decreases. Decreases are solely determined by the other parts of the model. In this case, it's the linear and quadratic term. Okay, so let's see, when ego is currently at 2, if ego is considering decreasing versus staying the same, even if the alters are at 1, that's not enough to pull ego to decrease as well. Ego is just as likely to stay the same. In fact, a little bit more likely to stay the same as decrease. For some of these others, we do see that ego is likely to decrease, but it's not so much peer influence that's driving that. It's simply the linear and quadratic term that results in ego dropping their score or decreasing their behavior. Okay. Now I want to look at one other scenario, and that's if peer influence is only present for decreases, right? Not increases in behavior. Okay. So here we have, again, if ego's at 1 and considering staying the same and decreasing, this is really hard to see actually, but this is the green line and gray line right on top of each other. Okay. So staying the same or increasing are solely driven by the linear and quadratic terms. Okay, and they're the same in each plot, right? The only thing that is happening in this model is that peers are influencing decisions to decrease. Okay, so when the red plot comes in, when ego is 2, the peers are going to pull ego down to 1. When ego is a 3, the peers are going to pull ego down to 2, and so forth. Okay. All right, so that's the conclusion of this part of the lab. I do want to iterate again the importance of understanding that the specification of peer influence is really important here. If we're going to use average similarity or different ways of specifying evaluation endowment effects, this is going to look very different, and the script will look very different. As well, make sure to, when you're considering looking at these advanced kinds of techniques and specifying more elaborate models, to really study the Siena manual. There's information about endowment effects in a couple of different sections of the manual. There's, as well as studying the effects themselves and how they're calculated. There's a couple of limitations on what you can do in terms of other model things. So for instance, one restriction is if you're doing evaluation endowment kinds of distinctions, that you have to specify actors coming and going in a different way. Structural zeros aren't compatible with this. Okay, that's detailed in the manual. So to make sure to take a look at that to make sure that your approach what you're doing here in the model specification conforms with what you're doing with the data specification. All right, good luck and happy modeling.
Thank you so much, David, for getting us started. I'm going to pick up with part 2 of the lab for today. That's going to focus on some advanced techniques for using simulations with SAOMs. Particularly what I'm going to focus on is a set of different kinds of techniques you can use to simulate what it looks like if you inoculate your participants. So here by inoculation, what I mean is kind of mimicking the effects of what would happen if we were to have a successful intervention take place among our actors in this network. So for instance, when we have interventions that are trying to do things like reduce adolescent drinking, typically kind of the goal of these intervention programs is to teach the participants a set of skills or impart in them a body of knowledge that helps them reduce their risky health behaviors and instead go on to lead healthy lives for the foreseeable future. So these inoculation techniques that I'm going to walk through today show you a way that you can simulate how these effects are actually shaping the social world. So to start off, here in my current R environment, I have all of the different are objects that was created in the first half of lab. So everything that David just walked through is still in my global environment here. Make sure that you also have all of the output from the first part of lab in your R environment, because we will be building off some of these models that we went through previously. So the first thing that we're going to cover is just kind of a standard simulation. This is review from the earlier lab that you all have seen on SAOM. At the end of that lab, David went through some examples of how you can use simulations in the Sienna package. So this is all just going to be a review of that, but we'll walk through this to make sure that we're all on the same page. So the first thing that we need to do in order to simulate the coevolution of networks and behavior is first we need to create a new Sienna effects object that looks exactly like that effects object that we created previously. So here we're going to do this by working with the myEffects1 object. So this was the effects object from that first model that we ran previously. This is the one that just treats pure influence as like the most simple way possible. So here we're not using we're not thinking about influence to increase and influence to decrease. Instead, we're just using the evaluation effect for influence. So let's go ahead and create a new effects object there. The next thing that we're going to need to do now that we have this new effects object is we need to set the initial values for each of these effects equal to those observed coefficients that we were able to estimate when we actually went through and estimated our SAOMs. So that's what this line of code is doing on line 188 here. What we're doing is we're pulling out all of the values from our results object that has the parameters for each of the coefficients saved in there. And then what we're doing is we're just adding that into the initial values of our effects object that we're going to use to inform the simulation. Another important step too is what's on this next line here. So it's really important that we make sure that these coefficients are fixed. We want them to stay constant because when we're using SAOM to simulate the coevolution of networks and behaviors, we want these effects to continuously shape what's happening over the course of the simulation. So that's what that next line of code is doing. And then to just show you all what's happening here. So now in the SimEffects1 object, so our effects object, you can see that we have all of these initial values. And then you can also see in the sixth column, everything is set to true. So that means that those won't be allowed to change. Instead, they'll remain constant throughout the simulation and continuously inform both changes to the network as well as changes to individual strengthening behavior. And if we look at our results from the model that we estimated in part one, you can see that these values for the estimates are the exact same as what these initial values are here. So right, when we estimated this SAOM, the coefficient for reciprocity was 1.99. You can see up here, the initial value for reciprocity is 1.99 as well. So again, we just kind of copied these over. So now that we've done that, we can go ahead and carry out the simulation. In order to do this, we're going to use the same set of functions that we used when we were estimating those SAOMs. So this should all look pretty familiar, but there are a couple new arguments that we're going to add in here that I'll walk through next. So first, just throughout this part of the lab, we're going to continuously do some simulations that include 100 iterations. This is just the number of the simulations that we do. By doing 100 iterations, that means that we're going to simulate 100 instances of the coevolution of this network and the drinking behaviors of the actors in the network. So here we're just going to work with 100, which is a relatively kind of small number of simulations. Typically, if you are doing this work to create a publishable piece of work, you probably will want to increase this to at least 1,000 iterations. But for the sake of time, we're just going to use 100 today. So next here, you can see we're using the Sienna algorithm create function, which is where we define what the algorithm is. And here you can see that we have a couple new arguments that we didn't have previously when we were estimating SAOMs. So first, right? The first two here are things that should look familiar, so we have to specify the project name. We can use the max degree argument to better fit what's happening in our network. But then starting here on line 198, you can see the in sub argument is now set to 0. What this is doing is telling Sienna that, okay, we only are interested in doing phase 3, which is the simulation phase of the SAOM models in Sienna. So this is just turning off kind of all of the earlier parts of an SAOM to make sure that we aren't going through and re-estimating all of our coefficients. Instead, we're just using observed coefficients and using that to simulate our network and behavior data. The next argument here is this in3 argument. And this is just where you specify the number of iterations that you want to simulate. So you can put a number here, but here we're just calling that in iter object that I created up here. And then finally, just to help you kind of save time and to make this process run more smoothly, you can use the sim only argument and set that equal to true. And what that'll do is it just skips the estimation of a covariance matrix because we don't need that information when we're doing the simulations. So that just will help you save time. So let's go ahead and run that piece of code. Now the next thing we do is we use the Sienna 07 function, which is where we actually estimate what's going on here. Here, this should look very familiar to what you've seen before. You don't need to specify anything differently when using the Sienna 07 function to inform a simulation. Instead, everything telling it that, okay, we're only simulating what's going on here is going to be saved in the algorithm output. So let's go ahead and run that. And you'll see that the little window with the Sienna information will pop up, but only for a very brief period of time, then it will finish. It is much quicker to estimate these simulations than it is to actually estimate the models. Then we can check out what's in our results to see what happened when we simulated. You can see here we have, again, the same information about the parameter values. These numbers are the same exact thing as those initial values that we specified earlier on. But you can see now we don't have any information about standard deviations. Again, that makes sense, right? Because we kept these fixed across every single simulation. So the parameter value across every simulation was the same thing. Therefore, we can't calculate standard deviations. This object also gives you some other kind of information too about what's going on in your simulated network. But typically, in order to extract the kind of information we're interested in, we'll have to pull out a couple different pieces of information from this object. So in the next couple lines of code, I have some examples of how to do that. So it's possible to pull out both the output of your simulated networks as well as the simulated dependent variable individual behaviors that you're interested in too. But here I'm just going to show you all how to pull out information about the individual's behaviors. Because here, right, we're interested in simulating interventions, and what we really want to change is those the drinking behavior of the participants of our intervention. So to do this, I'm first just going to create a vector where we can store a bunch of information. And then what I'm going to go do is using this for loop, I'm going to loop through every one of the 100 simulations. And from each of the simulations, I'm going to pull out information on each individual actor's simulated drinking behavior at the end of the simulation. So in other words, once the simulation is over, how much or what is the expected drinking behavior of each individual actor in our network? So we can do this by taking, by using this piece of code here. And essentially all this is doing is it's just walking through each of the individual simulations. So here, I'll show you all what this looks like. If we replace I with 1, this means this is the first simulation. And what it's going to do is pull out the drinking behaviors of each individual actor at the end of that first iteration. So here you can see we have 50 different numbers, one for each of the actors in our network. And each of these numbers represent that individual actor's drinking behavior. So in this for loop, we're just looping through each of these vectors and then taking the average. So we're calculating the average drinking behavior at the end of each of the different simulations. So here we can see what the output looks like, and you can see that here we have 100 just different elements in this vector, each of which tells us the average drinking behavior across all actors in the network at the end of the simulation. So now that we have this, right, remember that this was a really simple simulation where we didn't change any of our coefficients. Instead, we kept everything at its observed level. Thus, because of that, we should expect that our average drinking at the end of each of these simulations should look really similar to what we actually observed in our data. So here, if we go through and calculate what was the actual observed drinking behavior at time 2 in our data, that's what we're doing here in this first line. Again, by pulling out that data that's already included in the Sienna package. So the observed average drinking at time 2 was 3.1. The next, what I'm doing here is just taking the average of this vector of the mean drinking at the end of each of the 100 simulations. So on average across all of our simulations, the average drinking for the actors was about 3.1042. So right, not quite 3.1, but very, very close. So we can feel pretty good that our network's doing a pretty good job at the observed coefficients that we found are doing pretty good at kind of informing that process of the coevolution of drinking and friendship processes. So the next thing that I'm going to do is run another set of simulations, but here what I'm going to do is show you all how you could inoculate certain people in your sample. So in order to incorporate this inoculation element though, here is where we really need to start thinking about how Sienna centers our variables. So you all learned a little bit about this in the lecture, but before I kind of walk through this example here, I want to briefly show kind of what the arithmetic looks like that's going on in the background to help you better understand why we're going to have to walk through some of these steps here. So here I'm just showing kind of an example of what the centering looks like. This is one of the slides at the end of the slide deck from lecture if you want to reference this. And so here what's going on is say we're interested in simulating an intervention where we want to inoculate certain participants so that it reduces their risk of drinking by 2 units. So say, right, we had some individuals who partook in the intervention and the intervention was successful. And because of that, now their odds of drinking should be reduced by 2 units. So how could we model this? One way we could do this is we could start by creating an individual level binary variable that indicates whether or not each of the individual actors is inoculated. So that's this variable here called inoculated. Here, a value of 1 indicates that an actor is inoculated, while 0 means that they are not inoculated. Then what we could do is we could create a Sienna effect that accounts for how each actor's inoculation status shapes their own drinking behavior. So the way we would do that is we could use this inoculated variable, attach it to an effects from inoculation Sienna characteristic, and use that effects from inoculated characteristic to shape individuals' drinking behavior. So the dependent variable for individual drinking. And then the way that we can get this to decrease everything by 2 units, we can set the coefficient of that equal to be -2. So we already showed how you can go in and change each of those coefficients. You can set them to be that observed level. But for something that we didn't observe, like something that is occurring from this hypothetical intervention that we're interested in, we can go through and manually set the values of those coefficients. So that's kind of what we're thinking here. This all sounds kind of simple enough, but this whole process is complicated by this centering process. So by default, Sienna mean centers all independent variables and dependent variables. So I have an example of what I mean by that here. So right here is if we just had these 5 actors in our data set, this is their inoculation parameter. If we were to mean center this variable, what we would do is calculate the mean of these. Here, the mean is 0.4. So in other words, 40% of the individuals here are inoculated. Then in order to center each of these values, what we do is we take the actual observed value for each individual, and then we subtract the mean. So Someone who's inoculated, we would do 1 minus 0.4. That gives us a centered inoculation value of 0.6. For someone who's not inoculated, we would do 0 minus 0.4, and that would give us negative 0.4. So this is what our new centered variable would look like here in this column. And it's important to note here that now if we were to calculate the mean of what's going on here, we would get a mean of 0. So unfortunately, though, this makes things a little tricky, and it makes it hard to kind of model the inoculation effect, as I show here in this last column. So again, like I mentioned, we want to show that inoculation reduces one's odds of drinking by 2 units. So here the value of our coefficient is -2. So if we were to feed all of these different individual values through the equation, so we take -2 our coefficient, multiplied by each individual value for the centered inoculation coefficient, you can see here that now we're getting values that aren't quite what we expected. And this is because, again, of that centering process. So now because we centered the inoculation variable, someone who was inoculated, the way that the effect will reduce their odds of drinking is that it will only reduce their odds of drinking by 1.2 units. So here, right, instead of that whole 2-unit reduction, we're only getting 1.2 units. Similarly, if we look at those who weren't inoculated, here they're actually seeing a boost or an increase in their odds of drinking. So their odds of drinking increased by 0.8 units. So this is unfortunate because, right, it makes it kind of difficult for us to interpret our output and to interpret those average levels of drinking across the network after the simulation ends. So the reason that all of this centering happens in the first place is because centering variables really helps with the convergence of these stochastic actor-oriented models. But like David mentioned in lecture, using Sienna to simulate networks and behavior coevolution is a lot simpler, and it takes a lot less time to estimate. We also don't have to worry about convergence or goodness of fit or anything like that. So as a result, doing this whole kind of centering process really isn't necessary. So that being said, though, it's really tricky to turn off centering for the dependent variables in our model. We've figured out some ways to do this, but it requires that one goes through and creates new SAOM effects in the Sienna source code. So in order to do this, what you have to do is specify some new effects using C++, and then you need to install the Sienna R package from your own computer rather than from the CRAN or the way that you would typically install a package for R in either R or RStudio. So this whole kind of process is outside the scope of this tutorial. However, if this is something you'd be interested in doing, feel free to send us an email, and I can send you some kind of resources and code for helping you accomplish this. Luckily, though, it is a lot simpler to turn off the centering of independent variables. So I'm now going to switch back to the R script to show you all some tricks that we've developed as a way of how to effectively model this inoculation process. So now we're back in the R code with simulation 2 on line 224 here. So here, what we're going to do for our first simulation that incorporates this inoculation component, we're going to assume that our inoculation is only able to successfully reach those students who didn't drink at all at time 1. So these are individuals who their time 1 drinking is set to be 1, so the lowest value. So in our little fake data set of 50 students, this represents about 10% of the girls who are in the network, or 5 out of the 50. So not a ton of people, but let's go ahead and inoculate them and see what happens and see if that's able to kind of reduce our average drinking at the end of the simulation. So in order to do this, the first thing we have to do is again create that individual level variable that indicates whether or not each student is inoculated. Similar to like I did in that PowerPoint slide, here 0 is going to mean someone's not inoculated, while 1 means that somebody is inoculated. So we're going to create this variable, but It's important to note that this needs to be created as an array object in R. So we do this using the array function. And we're just creating an array that has the dimensions of the length of the number of students, and then has 2 columns in it. And the reason we have to specify this variable as an array is that we're going to set this to be a dependent variable in our SAOM. And Sienna just requires this format for all dependent variables. So in order to call something as a dependent variable, it needs to be an array to do this. So the next thing I have here is a for loop that what this is going to do is it's going to tell us which of the individual actors are inoculated. So specifically what it's going to do is go through all of the different actors in our network. For those who have those who didn't drink at time 1, they're going to receive a value of 1 for inoculated, while those who did drink at time 1, they're going to get a 0 for inoculated. So they're not inoculated. Again, only those individuals who didn't drink at the first time point are the ones getting inoculated. We also here can see that in the second, or what we're doing in the second column is a bit, you know, kind of interesting and different. So here, I'll pull up an example here, but so what's going on with the second column? The reason that I did this, so for every individual, if they did drink at time 1, they received a 0 for their inoculation status. But in that second column, I gave them a value of a 1. Similarly, for those individuals who didn't drink at time 1, they got a 1 in column 1, but in column 2, they got a value of 0. So when you use Sienna to create simulations, all that's taken into account is what's happening at that very first time point. So everything that's happening at in the second column, that represents the second time point, and all of that is kind of discarded because that information isn't necessary for informing the simulation. However, for our purpose, again, if we think back to centering and the mean centering, it can be kind of like, in order to just kind of make our math simpler, what we've figured out works well is if you take just the opposite value of the inoculation parameter and put it in that second column, it makes it so it's very easy to calculate what the average is of that inoculation parameter. So even though the simulation itself isn't using anything in the second column, all of this information is still being used in order to inform the centering process. So if we take the mean of that inoculation array, you can see that the mean is 0.5. So right, this is how this is what we would expect because right, we have the same number of 0s and 1s in this array. So as a result, 50% of the numbers in that array are 1, 50% are 0. So we know the mean of what's going on here, and we know how this is being centered. And 50% just makes it right kind of easy for us to know what's going on with our data as we move forward. So to further kind of show you all what's happening with this centering process, it's also necessary to create another individual level variable that's going to kind of help account for what's happening with the centering process here. So this variable is going to be called center, and it's not technically a variable because the value of the center variable for every single actor in this data set is going to be 1. So here is the center variable is just a vector of the number 1 50 times over and over again. And again, right, so this is just indicating that is the data for this individual centered? Yes or no? We know that every single person, their data is getting centered. So that's kind of what that's telling us. So the next thing that we'll need to do is create 2 new individual level variables and incorporate these into the Sienna data object. So the inoculated variable we're going to treat as a dependent variable. And the reason we're doing this is because we're going to simulate how the inoculation changes over time. So even the most kind of successful intervention programs that are able to inoculate their participants, these effects of an intervention often aren't permanent, but instead they kind of fade and eventually dissipate over time. Because of that, we're able to model that by treating the inoculation variable as a dependent variable. So we're going to do that here, just like how you would make drinking or smoking or any other kind of variable like that into a dependent variable for your SOM. The centering variable, on the other hand, we're going to treat as a constant covariate, so it's going to be an independent variable, and it's constant, right, because we're just going to treat it as being the same for the entirety of the simulation. But here, the important thing to note is that now we're bringing in the centered argument and setting that to be equal to false. So this turns off the centering for the independent variable. And this is really important because this is what makes it so we can make sure that all of our kind of math is lining up. As I mentioned before, right, it's really easy to turn off the centering of these independent variables. You just include this centered argument. Unfortunately, you can't add this same argument into the when you're using the Siena dependent function. It's just not a capacity that is supported by the Siena software. But again, we'll go ahead and make those two variables that are ready to be added to the Siena data object. Now we'll use Siena data create to add all of our different variables together. So this includes our friends and drinking variables that we worked with previously, as well as the inoculate and the centering variable that we just created up here. Now we can see that we have a variable that has three different dependent variables. So we have the friendship network is one of our dependent variables, and drinking is one of our dependent variables. This is all standard and the same as what you saw before. But now you can see we have another new dependent variable for the inoculated status of the participant. So like we did previously, what we're going to do next is create a new effect object that includes all of the same effects as we had in the SOM that we estimated originally. We're also going to need to create some new effects in order to model what's happening with this inoculation process. So I'm just going to walk through this because these are all the same lines of code that you saw previously. So we're just adding in all of the same effects. But now once we get to line 280, we're going to add some new effects that specifically have to do with the inoculation and the centering variables. So this in the first example, we're including an effect from effect for the inoculate variable. So here, even though inoculate is our dependent variable, here we're treating it like an independent variable because what this effect is going to do is tell us how does one's inoculation status shape their drinking behavior. So inoculate here is the independent variable, while drinking is the dependent variable, and that's why the argument for name is drinking, and then interaction 1 is inoculate. So using this effect, this is how we're able to model how one's inoculation status shapes their odds of drinking. Then the second effect is the centering effect. So here what we're doing is we're, again, creating an effect from effect, again, for the dependent variable of drinking, but this is how does centering affect one's drinking status. And that doesn't make much sense just saying it, but I will show you all when we add in the coefficients what this effect is doing. Essentially what this is going to do is account for the fact that the inoculated variable is not, or is centered, right? It's a dependent variable, so it is centered by default. We can't easily turn that off. So this variable helps us account for that. Now, if we look at the effects object, you can see that we have a couple new effects in here. So everything, the effects 1 through 11 should all look very familiar. But now 12 and 13 are those two new effects from effects that we just added in, one for centering, one for inoculate. And then we also, because we have a whole new dependent variable here. So by default, we're adding in this rate variable for the inoculated dependent variable, as well as the linear shape effect as well. So because we have these 4 new effects, we'll need to figure out what those initial values for each effect should be equal to. And then we need to set that initial value to the value that we think is going to best model the processes that are going on here. So for the rate inoculation, so this rate inoculate effect, right, that just tells us essentially how many opportunities each actor has to change their inoculation behavior by increasing it 1 step, decreasing it 1 step, or keeping it the same. So here what we've done is we set the rate inoculation parameter equal to be 1. So this means each actor is given an average of 1 opportunity to change their inoculation status. So here kind of the hope is that everyone will randomly be selected at one point and they'll have the opportunity to change their inoculation status. Again, because we know that the effects of being inoculated from an intervention are not necessarily permanent. Next, for this inoculate linear shape effect, what this is telling us is how does the individual's inoculation status kind of change over time. And what we've done here is set this to be a large negative number, so -10. If you have a larger network, so this is a pretty small network, 50 by 50, but if your matrix is bigger, you'll want to set this to be an even larger number. But the reason that we do this is because this makes sure that when any actor is given the opportunity to change their inoculation status, they will, like, without fail, decrease their inoculation status. Because, right, we know that you can't just kind of like magically become inoculated. Instead, you had to have participated in the program and it had to have been successful. So people can't increase their inoculation status, right? We only want to model that people are decreasing their inoculation status. So this large negative coefficient ensures that no one new is going to become inoculated all of a sudden. Then finally, the next effect, the effect from the inoculation. So this is our third effect here. This is where we can set how much the inoculation actually shapes one's odds of drinking. So in this example here, what I've done is I've set this to equal the negative value of the peer influence coefficient. So the reason I did this is we can think of this kind of simulation, or this simulated intervention. What it's doing is it's teaching those inoculated students a set of skills to resist things like peer pressure. So here I'm just pulling out from the result object the value of that the average similarity coefficient. And note that, right, the reason that's 11 is because the average similarity parameter is the 11th parameter in our SAOM, but it's not always going to be that 11th parameter. So you will have to change this in your own model to make sure that this is the size of the average similarity parameter. And then we have a negative sign in front because, right, we're inoculating students with skills to resist peer pressure from their friends. The next, finally, the effect from the centering variable. So here, right, again, the inoculation parameter is centered such that we subtract the mean from everyone's value of the coefficient. So, right, the inoculation parameter can be 1 or 0, and then we know that the mean is 0.5. So that means after the centering happens, someone who's inoculated has a value of 0.5, someone who's not inoculated has a value of negative 0.5. So because of that, we want to make sure that people are getting the full effect of the inoculation. So that's what this centering variable is going to do. So what we're doing here, because we know that the centering happens at 0.5, we're taking the same value of the average similarity effect, and we are dividing that by 2, and then taking and making it negative. So this is just ensuring that everyone who's inoculated gets the full dose of the inoculation. Then for those who aren't inoculated, what this does is it cancels out kind of that positive effects that we saw in that PowerPoint slide. So that's what this effect from centering is doing. So now that we have all these new coefficients that we can set as initial values for the effects, but combine all of these into a vector that compiles the coefficients in the appropriate order that they're listed. So what I mean by that is it's really important to make sure that all of the coefficients are in the same exact order that the effects are listed in your effects object. So yours might be in the same order, but they might be in a different order when you're working with your own data. Just make sure that they line up with what's in the effects object. And then here again, I'm just assigning the initial values for all of the effects and setting them all to be fixed so that they remain constant throughout the simulation. And now we can see that that was successfully done here. All of our initial values have been assigned and fixed is set to true for all parameters. So now that we've done that, finally we can carry out all of the 100 simulation runs. So here, this Sienna algorithm create, everything that's in here is the same as what was above. And then we just run everything through the Sienna 07 function. That should calculate really quickly. And then you can see we got some output. Now what I'm going to do is extract the drinking behavior for each individual actor at the end of the simulation run and use that to calculate the average drinking across all of the simulations. So this is the same code that I used to do this previously, but now we're going through this second set of simulations. So here's all the information here. Now, right, so our goal in applying an intervention and inoculating participants is that we want to reduce drinking to a lower level than we would expect to see had the intervention not occurred. So in order to see, okay, is this a good intervention? Like, is this actually going to reduce drinking a meaningful amount? What we need to do is compare the average drinking levels across the different simulations. So we can see here in our first simulation, we didn't change anything. We kept everything at its observed levels. Well, here what we've done is we've inoculated some participants. So we've changed kind of the rules of what's going on and what has happened in this network. So here we can see that when we inoculate the non-drinkers, the average drinking is 3.07. Where if we didn't inoculate anyone and instead kept everything at their observed levels, then our average drinking would be 3.10. So about a 0.03 reduction to the average drinking rate. This probably isn't a huge substantive difference, but remember again, right, we only inoculated 10% of the participants in this sample and only those who weren't drinking at very high rates to begin with. So we are still seeing that, right, the inoculation did appear to have an effect in the kind of direction that we would expect. Furthermore, though, so right, this is looking at everyone in our sample. So both the drinking averages of those students who were inoculated and those who were not inoculated are all being averaged together. So to better kind of see what these effects look like for those individuals who were inoculated, we can also pull out those individuals separately to kind of see how they hold up. So we inoculated them to resist peer pressure for drinking. So we'd expect that these individuals would have even lower drinking rates than they would be expected to have had they not experienced this intervention. So here in this for loop, I'm just pulling out the final drinking rates for those individuals who were inoculated at the beginning. And then if we take the average of that, we can see that on average at the end of the simulation, those inoculated participants had a drinking rate of about 1.32. So pretty low and close to 1, meaning most of them continued to not drink. But is this lower than what we would expect to happen to these participants, even if we hadn't inoculated them? So next, starting on line 331, what I'm going to do is go through the first simulation where we didn't change anyone. We didn't change anything. We kept everything at the observed levels. and go through, and for those participants who we inoculate in time 2, or in simulation 2, I'm going to go through and pull out what their expected drinking rate would be had no intervention occurred. So there, I pulled that out here, and now we can take the average of that. And here you can see that the difference becomes much more large and probably more substantively meaningful. So here, had there been no intervention, we would see that those non-drinkers at time 1, at time 2, their average drinking rate would be about 1.7. So a couple of them are starting to drink. Some are still remaining non-drinkers, but drinking is becoming more common among the subpopulation. Meanwhile, had we, if we were to successfully inoculate these individuals, we see a much lower drinking rate. So 1.3, that's about 0.4 units lower than had no inoculation and no intervention occurred. So next, I'm going to show you all one more example of a simulation that uses this inoculation technique. And here, just to kind of further demonstrate the utility of this technique and what it can accomplish, I'm going to show you all a kind of extreme example of what would happen if we were able to successfully inoculate all individuals in the sample. So say everyone, regardless of their time 1 drinking behavior, was inoculated in such a way that they were no longer, they were no longer susceptible to peer influence. So same kind of stuff that we went through before, but here what's going to be different is that data that we're going to put into our Sienna data object. So again, I'm going to create another inoculated object that's an array that's going to serve as the dependent variable for this simulation. Here, the for loop that goes through and assigns everyone their inoculation score is a bit more simple because every single actor is getting a value of 1 for their inoculation status at the first time point. And then as a result, that second column is going to be a value of 0 for everybody. And again, we do that in order to make our math easier for when we go through and account for the centering that occurs. So here you can see, right, everything in column 1 is a 1, everything in column 2 is a 0. We're going to create a variable for centering. Again, where here the value for each individual actor is the value 1, because right, this just indicates that that actor's inoculation parameter is going to be centered. So next, what we're going to do is create a new Sienna data object that includes both of these variables together. So we'll make inoculate a dependent variable, and centering is going to be a constant covariate. And then our data object will include these new the new inoculated variable as well as the centering variable. And then the friendship and drinking dependent variable behavior we worked with earlier. So in these next lines of code, we're just creating the effects object. This is the same as what I showed in the previous example simulation. Again, here we're adding the 2 new effects, so the effect from the inoculate on drinking and the effect from centering on drinking. And again, we're specifying the coefficient values for the 4 new effects. These are the same as they were in our second simulation example. So the effect from inoculation is equivalent to the negative value of the peer average similarity effect. So right, again, it's kind of the same idea as teaching students skills for how to resist peer influence. And then centering is half of that value because that affects for the way that the inoculated parameter was centered by the Sienna software. So next we'll assign the initial value for each of these effects and set those initial values to remain fixed. You can check that out, and everything should line up. And then finally, we'll use the Sienna algorithm create function and the Sienna 07 function to actually carry out our simulations. And now you can check this out, see that the simulations successfully ran. And now let's extract the drinking behavior for each of the individual actors at the end of the simulation run. So here, just like we've done before, we'll go through every single iteration and pull out every actor's drinking behavior at the end of the simulation, and then average all of this together. You can see we did that here. And then finally, let's compare this average drinking behavior to what we would expect to see in our other kind of simulated examples. So if we inoculated everyone in our sample at time 1, so if we taught everyone these kind of skills to resist peer influence, we would see that average drinking at time 2 would be about 2.32. Meanwhile, if we only inoculated the non-drinkers, so if we only inoculate those 5 actors who didn't drink at time 1, then our average drinking was about 3.07. So, right, we see quite a big drop here of about 0.7 units. So clearly, right, inoculating these participants is leading them to decrease their drinking behavior at time 2. And then finally, we can compare this to our baseline scenario where we kept everything the same as what was observed. And there, the average drinking at the end of the simulation was 3.10, which is very close to what we actually observe in the empirical data. So finally, here I have just some code 2 to kind of visualize these results. Just using kind of a simple box plot, this can help kind of help us compare what's going on in these different scenarios to see if the inoculation process that we're simulating is actually having a positive benefit on the drinking behavior of the adolescents in our sample. So here I'm just using different functions from the base R package to create this box plot. And here I'll make this larger for you all to see. You should get a box plot that looks like this, where here we're plotting the average drinking level across each of the different types of simulations. So our first baseline simulation where we kept everything at its observed level. Next, we have our simulation where we only inoculated the non-drinkers. And right from kind of visualizing this, you can see it's that right, the mean value does decrease a little bit, but in general, it's pretty similar to what's going on in the baseline scenario. And then finally, here we have what happens if we inoculate everyone in our sample. And here you can see that, right, this is a big difference. We see quite a decrease in the average drinking of the actors in our sample at time 2, so once the simulation ends. So by visualizing your results like this should help you kind of piece apart what's going on and which potential simulations that you are able to think of and which kind of like intervention processes are actually going to lead to substantively better outcomes for your actors. Thank you so much, everyone, for your attention. We hope that this tutorial was helpful and that you all learned a little bit more about some of the advanced techniques that you can use when working with SAOMs. If you all have any questions about the material that we covered in this tutorial, feel free to reach out to either me or David with your questions.